make or perform. We pay them tribute as we sing this song. Bacteria, chicka chicka. Bacteria, bacteria, chicka chicka. Bacteria.
We've got some great questions from the audience, and the first one, Rita, I think is for you, and that is, do you think that we are too hygienic today, and that contributes to health problems?
Well, having a couple of, actually 3 grandchildren, and every time I visit them, I come back with something from the kindergarten. I suspect that there's a mid-ground, where obviously you want to vaccinate against measles, mumps, and chickenpox, and that sort of thing. But on the other hand, I do think that this business of hand wipes and being afraid to touch doorknobs and that sort of thing is overblown. I would say that if there were an influenza epidemic, then I do think hand washing and very careful, even as the Japanese do when they have colds, they wear face masks. I think under those kinds of conditions, yes, we need to be very almost extreme. But under normal conditions, I think I probably, having been raised as one of 6 children, and in a time when my brother got the measles, my mother said, you might as well get it too and get it now. That maybe it wasn't such a bad thing.
Yeah, we had chickenpox parties when I was a kid. The next question, we have a wonderful quote from E.O. Wilson that I'd love to put up on the screen because this question connects to it. It says, what about co-evolution? Do microbes need us? And so here's E.O. Wilson's quote about our importance on the earth and ants' importance on the earth. Now that connects.
That puts us in our place, doesn't it?
Yeah, yeah. And then the question is, if microbes were to disappear from the earth, how long would we have?
Well, Ed Wilson, in one of his books, on the very last page, he said if he had to do it all over again, he would come back as a microbiologist.
How interesting.
Well, I would say if these cycles stopped, it would be all over. But it's unlikely to happen because
they're hardier than we are, it sounds
they
like.
are really hardier than we are. And the sun, I have a figure, I don't know whether it's worth showing now, that shows how the sun is getting hotter all of the time. And in another 5 billion years, it'll be too hot for any kind of life.
So we'll go to that planet that we've heard about, and the bacteria will take over here.
But the last organisms will be the bacteria and the archaea. So and they'll be there for another 3 billion years after we're gone.
But I guess with this question too, do microbes need us? Are we required for their life?
It would depend on the microorganism, because it's certainly true that many microorganisms live in concert with the animal, and if the animal dies, they die with the animal. So that's true.
Here's another question, and this may be for you, Jim. How far into the Earth's crust do microbes live?
That's an excellent question. This is one of the great research areas right now. There's a project called the Ocean Drilling Project, which is going down deep, and as deep as they've gone, they still find microorganisms. So it's quite amazing. So although you really can't see these microorganisms, except in very special places like Yellowstone, the actual biomass of microorganisms is more than that of the plants and animals on Earth. So, yeah.
That's astounding.
Yeah.
Can you talk more about the role of microbes in breaking down heavy metals and toxins? Is this something that we can count on microbes for?
Absolutely. We use microorganisms for breaking down toxic materials all the time. Now, in terms of heavy metals, they can't really destroy, elements and this sort of thing, but they can transform them. They can put them in states that are precipitable. For example, uranium in the soluble form can be precipitated with microorganisms, this type of activity. So materials like that are even radioactive can be treated by some microorganisms. In fact, there are some microorganisms that are radiation resistant. That doesn't mean that they can survive heavy radiation, but they can certainly survive much larger than what we could.
This, Rita, I don't know whether this is a question or something for a debate, but it's microbes and climate change, good or bad?
Microbes play a role in climate anyway. It's been shown that microorganisms in the atmosphere can actually be involved in precipitation. They produce dimethyl sulfoxide, and this interaction with moisture in the atmosphere and the microorganisms' activity, they play a role in rain patterns and rainstorms, and it's even been thought they could be used to seed clouds. So I don't think it's a question of whether or not they play a role in climate change. I think it's whether we can understand the role they already play, the many roles they already play. And I think, again, seasonality is a very significant phenomenon. As we rotate around the sun and as we have winters and summers, clearly there has been an evolution of life on this earth to adapt to that kind of pattern. And if we can understand it, then we can understand processes better on Earth.
I have to say, you all have the best questions. We've got some really great ones here to continue to get to. And this one I think is really interesting. Do bacteria get diseases?
Yes, very definitely. They are infected by viruses.
Yeah,
We haven't talked
much
about viruses. I'd forgotten that question.
They are often overlooked because they're not in the tree of life. They're not really cellular organisms with ribosomes, but they are extremely important, and they are, one talk today said that it's 10 times as many viruses in the marine environment as there are bacteria, as an example. So they're extremely important in transferring genetic material and all of this.
And we know they infect us, but they also infect bacteria?
Every organism that's been studied has a virus. Where they look for it.
But actually, they have the ability to shut down and just weather the storm, so to speak, and undergo what we used to call in the old days endogenous respiration. In other words, just enough turnover to just keep things kind of going until conditions are good again. And again, I think that is part of adapting to seasonal cycles.
That's what viruses can do?
A bacteria.
A bacteria can.
Yeah.
So if a bacteria is infected by a virus, it can shut most of its systems down.
Well, when it's under adverse circumstances, when there's not enough nutrient, or whether it's too cold or too hot or whatever.
I was hearing in a conversation yesterday of a couple of scientists, are bacteria's viruses called phages? Is that the term for them? Yeah. And they were talking about how when a bacteria is stressed, the phages leave like rats leaving a sinking ship, that they see that there's a problem and they jump ship to look for a better host.
But let's not get into an argument over whether viruses are living. That's a good PhD thesis defense question.
Well, I have to say that was one of the things that astonished me. I always thought viruses were alive, so it sounds like this is a conversation that can be continued. This is a lovely note. Your panel was excellent. I've learned a lot of great stuff, but how can we encourage young people between the ages of 13 and 19 to study our biodiversity and pursue sciences?
A couple of things. First of all, the valley of death in education is grades 4 through 8. That's when, especially girls, and now increasingly boys, get deflected from science, and especially mathematics. Mathematics is the most empowering of all subjects. It's the gatekeeper for all of the professional careers in science, engineering, medicine, and even for that matter, lawyers ought to be able to count. But I think that maybe they count too well. That may be another problem. But I think, too, I'll mention something that has happened recently that's very interesting. Eric Shivian, who's a Nobel laureate from Harvard, and Ed Wilson convened a very interesting meeting the end of November, beginning of December, of scientists. Jim Hansen, who's you probably all have heard of, who's very brave and has stood up for scientific principles. He's with NASA. Peter Raven, Jim Hansen, and a number of scientists met with the evangelicals. We met with Cizik, who is the head of one of the largest evangelical denominations. He has a very large TV audience. And we agreed that we didn't necessarily agree of how we got here, but we all agreed we needed to protect what's here. And so there was a press conference in January where the statement was made that whether you call it creation or diversity, that we all need to work together to protect this very important blue planet. It's the only one we've got.
Susan, I wanted to go back to this question to you because you've recently taught young people. And what do you see as the way to reach people in that age group, 13 to 19? I have to say, I went to my son's science fair yesterday. He's 11, and all of the kids were standing in front of their posters. And then I walked through the poster room here and thought, it's not that much different. And for the kids who love doing it in 6th grade, it's like you get to do that all the time.
Absolutely. I mean, I lived the life that I dreamt of as a 12-year-old, going out and playing in the woods. I still do that. I still get to go in the field and catch animals and study them. And I've had a lot of fun working with high school students who came in all last fall and teaching them about my research. And it's just really exciting when I can stand up and show pictures of me out in the field catching lizards and taking blood samples, and to see that recognition of someone saying, wow, I could do that for a living and get paid. You know, I could work in a place like this, come to work every day, walk through the dinosaurs, and just learn a lot about the exciting things that are out there in the universe. So I think just as being good quality scientists and being enthusiastic and communicating what we do, just like we're doing right now in terms of relating what we do to the general public, and especially to kids who are doing this, they're the guardians of the next generation for this planet. So.
We have a couple more minutes, so I'm going to go to a couple more questions. This is an interesting one. Given how hardy microbes are, is their existence in peril? Do we really need to concern ourselves with their conservation?
I'll take a stab at it. I think when we think about conservation of microorganisms, we're thinking about conservation of communities of organisms. For example, hot springs. These are relatively rare environments, and some of them have been converted into making thermal power plants and this type of thing. And you lose some diversity of these organisms when you do this. And so that is, I think, a real shame. But in general, we don't have the same kinds of concerns. Certainly, though, we know fungi can become extinct. There are problems with certain groups of them, I would say. But with most of the bacteria, we're not too concerned about that as an issue. Rita, you may want to elaborate a little bit.
No, I think you're right on target. It's a matter, really, of maintaining the balance of the community structure that is so protective of life. Actually, we don't really lose necessarily microbial species. We simply suppress and we shift populations by adding excess nutrients, pollutants, whatever. And as was described in the example this morning, when you withdraw it, then you get the population sort of resuming its natural mixture. I think it's critical to understand what those mixtures are, what comprises them, and then what maintains their stability. These are the kinds of things that we don't know much about because we live in what I call the Nobel Prize distortion. You get a Nobel Prize if you study the structure of an enzyme, its folding and its electron structure of one enzyme on the one leg of a centipede. You don't get a Nobel Prize for understanding how that centipede interacts with all the other centipedes and with higher animals and how the system works. And therefore, there's this contortion toward reductionism, ultimate reductionism. And now we really need holistic approach. We need the kind of understanding complexity. And ironically, mathematicians are ahead of us. Mathematicians have been intrigued by complexity, and there's a whole area of research in mathematics called complexity. And now we really need to understand biocomplexity or systems biology. I don't care what you call it, a rose is a rose is a rose. But we need to understand how it's integrated. So you're right on target.
It's interesting to hear you talk about that. Here we are talking about the tiniest of organisms on Earth. And what's really important is not looking just at them, but to look at how they connect to everything else. Well, thank you so much. This has been such a pleasure to hear what you have to say about this subject. And thanks to you for these great questions. We're going to get a chance to leave you with a little artistic expression about microbes. This is Esther, Francis, and the Holographic Donuts, yes, which Susan found for us, so you can take a listen. Here. Esther is here if you want to talk to her about her inspiration from bacteria and other kinds of microbes. Thanks so much to Susan Perkins and Rita Colwell and Jim Staley.
Thanks.
Cosmic kettle of life on Earth is filled to the brim with you. Bacteria, chugga chugga. Bacteria, bacteria, chugga chugga. Bacteria. It's time to appreciate the microchemistry that is the key to our sustainability. Billions of years before we were born, microorganisms sang the song. Bacteria, chugga chugga. Bacteria, bacteria, chugga chugga. Bacteria. Humans think we're at the top of the heap, yet we never ever could be complete without these tiny creatures that make up our form. We pay them tribute as we sing this song. Bacteria, chugga chugga. Bacteria, bacteria, chugga chugga. Bacteria. $3.5 billion years ago, bacteria came forth to join the show. 8 million years later, crisis arose. Imagine, oxygen was the foe. Here's how the story goes. Oxygen was a poison long before we had a nose. Bacteria adapted, learned how to breathe it. Because of them, we are here to sneeze it. Bacteria, chugga chugga.